My name is Andre Horvat, and today I would like to discuss a simulation methodology based on computational fluid dynamics, CFD, for assessment of spills of liquefied natural gas, LNG, onto water. The work was initially presented at Shell in Ellesmere Port and then in substantially expanded form published by Process Safety and Environmental Protection in 2018. The presentation is organized in 7 sections and it closely follows the recently published paper. In the introduction, we will look at objectives for the presented work and discuss the framework of the commercial project that initiated the development effort. The LNG release scenario will be discussed next, although the conditions of the scenario may be specific for the described case. The developed simulation methodology is general and therefore suitable for much wider selection of cases. Dynamics of the LNG layer deserves special attention as it determines the initial distribution of the LNG. We will discuss modeling approximations of the LNG source, that is the impingement point onto the water surface, spreading of the LNG liquid layer, and exchange between the LNG liquid layer and the ambient, that is gaseous environment. Low temperature of the stored LNG leads to boiling at its release, and at favorable condition even to rapid phase transition. The associated regimes, that is film boiling, transition boiling, rapid phase transition, and nucleate boiling, will be presented in detail in the next section. The last modeling stage, although the least complex, is dispersion of gaseous LNG in the ambient. Once the modeling methodology has been fully described, we will look at the CFD simulation results. This will include flammability limits and the volume of the flammable cloud and overpressure approximation due to rapid phase transition. At the end, besides specific conclusions related to the assessed cases, a broader discussion on future challenges will be outlined. The aim of the current contribution is to present simulation methodology that has been specifically developed for a mainstream commercial toolset. The discussed models are able to simulate behavior of LNG spills from the initial release, spreading on the water surface, rapid phase transition to subsequent dispersion. Although individual phases has been addressed before, the robustness of the combined approach is unique. A complex release scenario studied in a framework of a commercial project is used to illustrate individual phenomena, related modeling assumptions, and the model behavior. The project focused on the behavior of an energy spill between a floating LNG vessel and an LNG carrier in order to calculate the size of the flammable cloud and to determine the resulting overpressure due to an RPT event. These topics are of particular interest to deterministic risk assessment in the expanding LNG sector. Intentionally, I will use the project results in a highly selective manner to demonstrate modeling principles, but to avoid commercial sensitivity of specific findings. Nevertheless, basic mathematical formulations of fluid dynamics and heat transfer that can be found in any CFD manual may be referenced, but will not be repeated. In the analyzed scenarios, an LNG carrier is moored alongside an FLNG vessel. The figure shows a general layout of the vessels, their size, and the location of the loading arms. Proximity of both vessels importantly determines the shape and the propagation rate of the LNG layer and the subsequent form of the gaseous cloud. The simulation results that I'll present and discuss are for the case where a failure in the FLNG process train leads to an LNG release with a mass flow rate of 1020 kg per second and the duration of 76.2 seconds. The release is at a height of 20 meters. The LNG composition was agreed with the client to be a hydrocarbon mixture of the following component mass fractions: 78.76% of methane, 12.31% of ethane, and 8.93% of propane. The sea and the air temperature were set to 25 degrees Celsius, with a wind speed of 0.5 meters per second at the reference height of 50 meters. Simulation of such an LNG spill scenario requires an adequate modeling description, that is, formulation in its numerical implementation of liquid layer behavior, compressible effects associated with the RPT phenomena, and dispersion of gaseous LNG in ambient air. Each section is associated with certain modeling challenges, which will be discussed in detail in two subsequent sections. Dispersion simulations command the use of large simulation domains to predict cloud behavior. On the other hand, a liquid layer that serves as a source of gaseous cloud is usually just a few millimeters or at most a centimeter thick. For that reason, very fine grid spacing is needed to directly resolve the liquid layer. In addition, local liquid surface instabilities do require use of small time steps, usually below 1 millisecond. These constraints make such CFD simulations prohibitively expensive. The solution is in two-dimensional approximation of the liquid layer, which is coupled to a larger three-dimensional ambient domain for dispersion analysis. For that purpose, a commercial CFD code, Flux, incorporates a shallow water-based model. When general-purpose CFD codes are used, for example Fluent or CFX, a multi-phase formulation is required. Figure shows such decomposition of the simulation domain for a simple test case. A thin 2D multi-phase domain that is occupied by LNG and air is placed below an ambient domain with a variable composition mixture of gaseous LNG and air. The present work is based on a multi-phase formulation of the liquid layer, and therefore applicable in most of general-purpose CFD codes. In a 2D multi-phase domain, a liquid fraction R LNG is defined. It substitutes the shallow water formulation and relates the thickness of the LNG layer, H LNG, and the height of the 2D domain, H layer. The rest of the multi-phase domain, expressed here with 1 minus R LNG, is occupied by the entrained air that has the same velocity as the liquid phase. This detail is important in order to preserve continuity of both phases. Let's look first at source approximation. The LNG release height, HREL, determines the velocity of the liquid at the point of contact with water due to free fall acceleration. Higher is the location of the initial release, larger is the liquid velocity at impingement. The main assumption is that kinetic energy of the impinging jet is preserved, and that no additional surface mixing significantly decreases its flow velocity. This affects the LNG spreading rate and thus represents a conservative assumption. Namely, a higher spreading rate leads to a higher rate of evaporation and therefore to a larger cloud of gaseous LNG. The initial point of a spreading LNG layer can be defined as a volumetric source over a certain area with the diameter d source. The LNG volume fraction that is calculated depends on the mass flow rate of the release, m dot LNG at real, the liquid velocity of impinging jet, u LNG at source, and the selected diameter, d source. Although the diameter d source is an input parameter, it only defines conditions inside the source volume. Outside the source, the liquid volume fraction, R LNG, and the related height of the liquid layer, H LNG, are independent of the source size and of the domain layer thickness, H layer. The figure shows the location of the liquid layer source between two vessels. The selected diameter of the source was 0.8 meter, or twice the reported release diameter. To maintain the same level of kinetic energy, the following equality for the impinging velocity applies. If we insist to maintain the same level of kinetic energy of the impinging LNG jet, Without any significant mixing with water and no hydraulic jump, this relationship also fully determines the appropriate height of the liquid simulation domain, H layer. Next, we will look at spreading of the liquid layer. Spreading rate of the liquid is calculated using a multi-phase formulation of the mass transfer equation, where R LNG is the LNG volume fraction. The term on the right-hand side of the equation is applied in the source volume only. It should be noted that a complementary transfer equation for the ambient air volume fraction is also required to maintain the volume fraction ratio and the related LNG layer thickness. For the presented model, the homogeneous multiphase formulation was selected. This brought an additional resistance to the liquid layer dynamics, but the conducted tests did not produce large differences in comparison to the heterogeneous model. Figure presents the liquid volume fraction distribution 20 seconds from the start of the release for one of the conducted tests. Higher volume fraction near the progressing front clearly showed the hydraulic jump and the initial jet atomization. The next important topic is domain interface exchange. The liquid layer domain is coupled to the ambient domain through source terms. On the liquid side, these are volumetric source terms to model the LNG phase change and to maintain two-dimensional approximation. For the ambient domain, the source terms are associated with the interface surface only. The mass exchange between the liquid layer and the ambient domain was modeled as an asymmetric process. Only the mass associated with the LNG boiling was allowed to appear at the ambient side in exactly the same extent as it was removed from the liquid layer domain. Any other mass exchange is considered to be negligible. To understand these mass transport equations, it is important to explain that Yk represent mass fractions of the gaseous LNG components and air, rho amp is the density in the ambient domain, and J evap is the mass flux associated with the LNG evaporation. As already mentioned previously, gaseous LNG is modeled as a fixed composition mixture of methane, ethane, and butane. Because of liquid layer domain two-dimensionality, the flow conditions are much more sensitive to any mass source or sink than the ambient domain. For that reason, the volume outflow rate associated with LNG boiling in the liquid domain has to be compensated with an equal volume inflow rate of the surrounding ambient air. Thus, the following source term was added to the transport equation for the ambient air volume fraction in the liquid domain. As the liquid spreads, it supplants the gaseous phase around the domain. Because the domain is closed in the vertical direction, any movement of the gaseous phase has also a profound effect on the shape of the liquid phase. Such behavior is a modeling artifact due to the two-dimensionality of a liquid layer modeling approach. In reality, the ambient air is exchanged or entrained in the vertical direction perpendicular to the liquid layer. To introduce the vertical exchange of ambient air to the liquid layer domain, additional source terms were also added to the momentum transfer equation for the gaseous phase. The first term on the right-hand side removed the accelerated gaseous flow from the simulation domain, whereas the second term replaces it with the same amount of zero velocity ambient air. It's important to note that the additional source term for modeling the entrainment process are only required due to the multiphase formulation that includes the liquid as well as the gaseous phase in the two-dimensional layer domain. If the utilized CFD code allows modeling of the liquid phase without the feedback effect from the gaseous phase, using for example shallow water or volume of fluid based models, such additions are not required. Figure shows the results of a model test using a constant LNG evaporation mass flux of 0.2 kilograms per meter square second. The selected value complies with observations described in the literature, although the LNG evaporation rate will be addressed in great detail later in the text. The test was performed for the same release parameters as described previously. The thickness of the LNG layer, which is shown 80 seconds since the start of the release, is the highest near the source. It decreases uniformly toward the progressing front due to the constant evaporation mass flux used in the model. The saturation temperature of LNG at atmospheric conditions is minus 162 degrees Celsius. This means that in contact with water it starts to boil. There has been a lot of research in different LNG boiling regimes, mostly to accurately determine the associated evaporation mass flux. The values between 0.02 and 0.3 kilograms per square meter second have been recorded by different research groups. In the initial tests of the presented work, a single value of 0.2 kilograms per square meter second was selected for the LNG evaporation mass flux. Such coarse approximation cannot be used to model the rapid phase transition phenomena, or RPT. To capture RPT, different boiling regimes and the associated evaporation mass flux have to be introduced in the modeling procedure. Rapid phase transition, or RPT, is the result of the LNG layer superheating. When the maximum superheating limit, that is, the spinodal state, is reached, the accumulated thermal energy is released instantaneously by a rapid phase change from liquid to gas. As a result, a pressure wave is formed that propagates through the ambient air. Figure shows the LNG temperature enthalpy diagram with marked initial saturation conditions, superheating, resulting RPT, and further heating of the gaseous LNG. The phase transition diagram does not reveal different boiling regimes with the associated evaporation mass fluxes. A boiling curve relates the temperature difference between the surface and the LNG layer with the resulting heat flux to the LNG layer, QEvap. It was reconstructed from diagram published by Melem and collaborators in 2006 and Verzik and collaborators in 2009, although in both instances the work is based on much older data. Once the heat flux is calculated, the associated evaporation mass flux is obtained by simply dividing the heat flux with the LNG latent heat of evaporation. In the current analysis, an average value of 641 kilojoules per kilogram was calculated from a previous review study. In the present case, the water temperature is 25 degrees Celsius, resulting in a temperature difference of 187 degrees Celsius for the LNG water contact. Such high temperature difference facilitates film boiling. The temperature difference starts to decrease as the water surface cools down and freezes. Thermal state of the water surface is not directly included in the current model, which means that it needs to be approximated by an empirical correlation. The evaporation mass flux decreases with the contact time. Its maximum, Jmax, is reached at the point of the initial LNG jet impingement, when direct contact between LNG and water still exists. This brings additional complexity, as the local contact time needs to be tracked and recorded during the CFD simulation. To track the contact time, the following equation was used, where delta is a small threshold number. Based on the experimental data of the US Coastal Guard for a similar LNG composition, the following linear function was implemented for the evaporation mass flux in the film boiling regime. Figure shows the local distribution of the evaporation mass flux due to the contact time dependence. It is clearly visible from differences in the evaporation rate that it decreases with the contact time between LNG and water. The propagating front has the highest evaporation rate, which fades downstream as the spill progresses. The vapor film collapses when the temperature difference T water minus T LNG decreases to approximately 70 to 80 degrees Celsius. At that point, the LNG comes into a direct contact with the water surface. As the LNG layer is at its saturation temperature, the lowest temperature difference is essentially determined by the minimum surface temperature T water. Combining the boiling curve for the film boiling regime and the evaporation mass flux as a function of the contact time allows us to determine the time needed to reach the LNG boiling crisis based on the minimum temperature requirement. When the local contact time exceeds the critical, the heat flux from the water to the LNG layer increases to Qmax. At present, this was set to 300 kilowatts per square meter, although some authors reported even higher values. This transition between the film and the nuclear boiling regime is quick, but only a part of the available heat transfer to LNG can be continuously utilized for the LNG evaporation. If Jmax is the maximum evaporation mass flux that arises from the direct contact between two phases, then the difference is used for the LNG layer superheating. This causes the temperature of the liquid layer to increase, eventually leading to an RPT event. Figure shows the local distribution of the evaporation mass flux when the transition boiling regime with the liquid layer superheating is included in the CFD simulation. Although the front of the progressing LNG layer still experiences film boiling, the center of the LNG layer managed to cool the water surface to the point where the transition boiling regime starts to occur. When the LNG liquid layer reaches the maximum superheating temperature, Tmax, it triggers an RPT event. In the present model, Tmax was set up to 191 Kelvin, as proposed by Mellem for a similar LNG composition. During an RPT event, the sensible heat that is accumulated in the form of LNG superheating is suddenly released, causing rapid evaporation. The first equation represents transport of LNG mass in the liquid layer, and the second the related enthalpy of superheating. Sinks of mass and energy associated with evaporation are marked with red. The evaporation process finishes when H super decreases to 0. The resulting mass flux is high but not infinite. It has to be limited by the sonic speed of the surrounding gas. Although the composition changes as the LNG evaporates and mixes with the surrounding ambient air, the material properties of gaseous LNG were used to determine the evaporation mass flux, JRPT. Figure shows the evaporation mass flux, JRPT, during a simulated RPT event. Areas of high level evaporation mass flux are associated with the ongoing RPT event, whereas the low mass flux indicates film boiling due to continuing LNG release. Once the thermal energy associated with LNG superheating decreases to 0, the RPT event also concludes. It is assumed that the remaining LNG is well mixed with water and therefore evaporation continues in the nucleate boiling regime. Due to a low temperature difference between the LNG and water, a direct contact between LNG and water becomes possible. For that reason, the maximum evaporation mass flux can be assumed, which is in this case, as I mentioned previously, 0.38 kilograms per square meter second. The evaporation mass flux is transferred from the liquid layer domain to the gaseous ambient domain using the source terms on the right hand side of the mass transfer equation, where Yk are mass fractions of the gaseous LNG. The imposed wind velocity field disperses generated gaseous LNG. Figure shows the initial velocity field for the imposed wind speed of 0.5 meters per second. It has to be noted that dispersion of gaseous LNG cloud mostly depends on its buoyancy. At the beginning, the gaseous LNG is at its saturation temperature, that is at minus 162 degrees Celsius and is therefore negatively buoyant. Due to its high density, it freely flows above the water surface. The cloud needs to heat up above minus 108 degrees Celsius to become positively buoyant. It is buoyancy that lifts it up from the water surface and strongly enhances its dispersion. The heating process is controlled by mixing with the surrounding air. Figure presents a dispersing LNG cloud after 320 seconds. The orange isosurface marks the gaseous LNG mass fraction of 10%, whereas the yellow isosurface shows the mass fraction of 1%. The CFD model was prepared in the ANSYS CFX simulation environment, mostly because of simplicity to add different model extensions. Although a number of different scenarios were analyzed, the results will be presented only for the process train release case that was fully defined previously. Two main analysis objectives are discussed and visualized: volume of the flammable cloud and its distribution, and overpressure approximation due to RPT. The animation shows the development of the gaseous cloud. Two isosurfaces illustrate volume fraction of the lower and the upper flammability limit at 25 degrees Celsius, that is 4.5 and 50% respectively. The diagram presents the integrated flammable volume for two analyzed cases. It shows that the maximum cloud volume reaches 1 million cubic meters. The CFD analysis shows that the gaseous LNG remained present between both vessels long after it has been dispersed from more wind-exposed areas. Notice a vertical line that marks the duration of the LNG release. This delay in growth of the size of the cloud is due to negative buoyancy of the gaseous LNG and the time required for the cloud liftoff, which is mostly independent from the duration of the initial spill. The extent of an RPT event is constrained by the LNG layer superheating. As such, it does not involve a significant amount of LNG. Therefore, its effect on the dispersion process of the gaseous LNG is limited. Previous figure shows that the time variation of the flammable volume is practically unchanged by the RPT event. The most important manifestation of the RPT event is a pressure wave that is formed. It propagates through the ambient domain with the sonic speed. The animation shows an overpressure isosurface of 400 Pascal. It visualizes propagation of the pressure wave through the ambient. More revealing is a cross-sectional view of the calculated overpressure field. The overpressure is high at the beginning, close to the LNG layer, and decreases with radial expansion of the pressure wave. The shape of the propagating wave is importantly influenced by both vessels. They represent an obstruction, which leads to local pressure wave reflections. Figure presents time variation of maximum overpressure. It shows that the maximum overpressure exceeds 110 kilopascals. Although similar pressure peak values have been already reported, large variations can be found due to differences in experimental conditions. The pressure peaks occur close to the water surface, where the temperatures are close to the LNG saturation temperature of minus 162 degrees Celsius. This combination of high pressures and extremely low temperature does pose a significant risk of structural failure. The paper presents a CFD modeling approach to simulate the behavior of LNG spills from their initial release, spreading on the water surface, rapid phase transition to subsequent dispersion. The described approach is generic and can be used in most of the available CFD codes that include multi-phase flow capabilities. It has to be admitted that many modeling simplifications, especially in formulating the effects of different boiling regimes, were utilized by using available sources discriminatorily. In most of the review cases, the modeling relies on a single source of the boiling curve definition. Until more complete data is available, this will remain the weakest point in any modeling approach. The energy transport equation was not used in modeling the LNG liquid layer to avoid the definition of the heat transfer between the water and the liquid layer. Such definition would have to involve, or at least quantify, the effect of ice formation and its thickness, state of the surface, and any convective mixing. The presented CFD simulation results demonstrate the capability of the developed methodology. They are related to a failure in a floating LNG process train that led to an LNG release in a highly constrained space between two vessels. The analysis methodology allows to estimate the size and distribution of a flammable cloud generated by the LNG spill. The simulation results identified an important behavior. Due to negative buoyancy, the flammable cloud initially spreads in horizontal directions. For that reason, it does not reach the process decks, which significantly lowers the fire-related hazard. The overpressure prediction due to an RPT vent shows that the maximum exceeds 110 kilopascals. Such high pressure in combination with low temperatures, that is, minus 162 degrees Celsius, may lead to a structural failure of the vessel hull. It is important to emphasize that further parametric studies are needed to determine the sensitivity of the RPT-induced pressure peaks to the size of the LNG release, speed of evaporation, and ambient temperature. I would like to thank you all for your attention. I hope you found the lecture interesting. For any specific question, please do not hesitate to contact me.